So in this video, we want to look at what happens when you have multiple qubits. So as you remember before, any two-state systems, classical two-state systems, we could call that a C-bit. Any quantum two-bit systems are called qubits. And they could be our electrons with our sensors measuring up, down, right, lefts, or it could have been with our polarizers with photons, whether you get through the polarizer or you don't get through the polarizers. Those are both two-bit systems. There are other two-bit systems, but those are two of them. But what I wanted to say is, what happens if we have more than one qubit? So let's just say we have a qubit right here, psi 1. And it's equal to, alpha 1 up plus, say, alpha 2 down. Okay, and you remember with C-bits, you're either a 0 or a 1. You're either an up or you're a down. You can't be, but with qubits, remember, this squared is the probability. You could be 10% up and 90% down, or you could have been 52% up and 48% down, or all possible combinations. They're all in here. So you can see how much more powerful they are than just being up and down. And then let's say we have a second qubit, which is, say, beta 1. Up plus beta 2 down. Again, we can't really ever know what alpha 1 is or alpha 2 is. The only way you could ever figure it out is if you had a whole bunch of identical ones and then you measured the average or the probability that you get up, and took the square root of it, that's what you get for this. But you can't just from this one, you can't get alphas and the betas. Okay, but now let's say we combine the two together. When we combine the two together, they become a composite system. So they become composite system. Okay, and so, well, how do we combine the two right here? Well, we multiply them together. So we get psi 1 and psi 2. Now, we multiplied vectors in classical mechanics. We started out with a dot product. When you dotted them, you got a scalar. And then we went to a cross product. When we did the cross product, we got a vector. But we're going to be multiplying even a third way right here, which is called a tensor multiply. And we use this symbol right there. That means tensor multiply. Tensor multiply. Okay, so how do you tensor multiply? Well, what we do is we write them out. Let's just write it out first. Alpha 1 up plus alpha 2 down, tensored with beta 1 up plus beta 2 down. Okay, you still FOIL it out, just like you did before. So this times this is alpha 1 beta 1, except when I multiply this tensor multiply, it really becomes up, up. It just sticks with up, up. Or if you want to write it a little bit more compact, I don't need so many, I could just write it as up, 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 up. Plus this times this, which is alpha 1 beta 2 up, down, up, down, plus this times this, which is alpha 2 beta 1 down, up, And then the last one, alpha 2 beta 2 plus alpha 2 beta 2 down, down. Now, what this really means is this up corresponds to the first particle, and the second up corresponds to the second particle, right here. So this is the first particle's up, the second particle's up, first particle's up, second particle's down, first particle's down, second one's up. Here, they're both down. So you don't change the order of this. This is always for the first one in your tensor, and this is always the second one. Now, this is just a constant. It's just multiplying two complex numbers together. It's still a complex number, so why don't I just call that one symbol? We could just call it, say, alpha 1, 1, up, up, plus alpha 1, 2, 1, 2, up, down, plus alpha 2, 1, down, up, plus alpha 2, 2, down, down. Now also, the space, the dimension of the space, these were each just 2 dimensions, and this is a 2 dimensions. But when you do a tensor multiply, you multiply their spaces. Now it's a bigger space. This is a 4-dimensional space right here. If I wanted to, now this thing's got 4 items in its column. Up, up, what would up, up look like? Up, up would be, there's my first up, there's my second up, you see? So up, down would be 1, 0, 0, 1, and so on right here. So this is now a 4-dimensional space. So when you multiply, tensor multiplying, you're making the space bigger. Also, remember, this squared, alpha 1, 1 squared, is the probability that the first one is up and the second one is up. This one right here, alpha 1, 2 squared, is the probability that the first one's up and the second one's down. And this one over here, alpha 2, 1 squared, the first one is down, the second one's up. And alpha 2, 2 squared is the first one down and the second one down. And when I add these up, it should be normalized, because those are the only things that can happen. This should be 1. Just like up here, this magnitude squared plus this magnitude squared is 1. But here, it's down here. Okay. Well, what if we had, say, 3 qubits? If we had 3 qubits, then you'd have, say, psi 1, psi 2, psi 3. Okay, maybe psi 3 had gamma up plus gamma 2 down. Gamma, maybe psi 3 was equal to gamma 1 up plus gamma 2 down. Well, if I multiplied all that, then I already multiplied 2 of them. I got 4 terms. And then if I multiply this whole thing times my psi 3, then I have to multiply each one by all of these. So that means I'm going to get 8 terms. So I'm going to get 8 terms here. I'm going to get something like a gamma. Well, when I multiply this by that right there, I'm going to get a gamma 1, 1, 1. Sorry, alpha 1, 1, 1 up, up, up. So, so I'm going to get alpha 1, 1, 1. I'm going to have 3 terms. And then I'd get like an up, up, up. And then when I multiply this times this, you get a alpha 1, 1, 2 up, up, down, plus alpha 1, 1, 2 up, up, down, plus. And this is going to be 8 terms. I'm not going to write them all out, but there's going to be 8 terms here. This would be an 8-dimensional space right here. Oh, okay. So it looks like the number of terms that I get here really goes as 2 to the n, where n is how many I'm multiplying. That's how many terms I get. So, well, let's say you had, say, 300 electrons put together. And now I have a big composite system of 300 electrons. So I'd have psi 1, psi 2, psi 3, psi 4 times all tensor multiplied for all the way up to psi 300. And then you say, how many terms do I have? Well, I would have 2 to the 300 terms. I'd have 2 to the 300 terms. How big is that number? 2 to the 300. Well, 2 to the 3 is 8, close enough to 10. So 2 to the, let's just say 2 to the 3 is around 10 for a minute. It's not, it's really 8, but it's close enough. So this is around, since I'm multiplying this by 100, this would be about 10 to the 100. Well, there's only 10 to the 80th electrons in the universe. 10 to around 80. That's how many electrons. And even if you add up all the photons and the protons and every other particle in the universe, there's not going to be this many particles right here. So just 300 qubits put together, 300, you couldn't even see that, has more terms than the number of particles, counting photons, in the entire universe. And nature really has to keep track of all these terms. Nature has to keep track of all these 10 to the 100 terms because these determine the probabilities of what happens. So nature has to be quite, we're only looking at 300 electrons. Think of all the electrons in the universe. I don't know how it keeps track of all of those terms because it has to determine the probability. Well, we call this state, well, maybe I'll just keep it right there for a minute. This one, either one of these two, we call it, at least for these two, right, this one right here, we call it a product state. Why? Because it was the product of two. We might even call the third one a product state, as long as you can factor it down. See, I could take this and factor it back to this and this, and so they call this a product state. Product state. But there are some terms, there are some states, two system states, composite systems, that are not product states. What does that mean? That means you can't factor them. Let me give you one example right here. How about psi equals 1 over the square root of 2 up, down, minus 1 over the square root of 2 down, up. That I can't, that would mean that this term is 0 and this term is 0. I only have the inner terms right there. We know it's normalized because the first term squared plus the second term squared is 1. But the reason why I can't factor it is because if you just compare it to this term right here, that would mean since this term has to be 0, that means alpha 1, beta 1 have to be 0. Alpha 1, beta 1 would have to be 0 if I was going to factor it. And likewise, this term, there's no down, down up there, so alpha 2, beta 2 would also have to be 0. And this term, up, down, is going to have to be 1 over the square root of 2, so alpha 1, beta 2 is equal to 1 over the square root of 2. And the last one, this one over here, alpha 2, beta 1, would have to be minus 1 over the square root of 2. Alpha 2, beta 1 would have to be minus 1 over the square root of 2. So that would have to happen for this to equal that. And you'll notice right here, this tells me that either alpha 1 has to be 0 or beta 1 has to be 0. Now, if alpha 1 is 0, then you come down to here, it can't be, because then you get 0 there. Or beta 1 has to be 0. If beta 1 is 0, then this should be 0. So you can see that these are completely inconsistent with this right here. So there's no way I could ever factor this into these two states right here. So this is a special state. Sometimes they call these Bell states. Bell states. Or one you've probably heard more of, and that is quantum entangled states. Entangled state. Right here. So it's a quantum entangled state right here. You'll notice if you measure the first one here and you get up, well, then the second one has to be a down, because there is no down, there is no ups right here. There's only an up and a down. So if whatever you measure the first one, the second one has to be the down. You notice over here, if you measured the first one up, then you would be left with these two states, because these two downs would have been gone, and you'd just be left with this without the up. Just take that away, and you'd just be left with some constant up plus some constant down, where that's the second one. If you measured the second one and it was a down, then you'd just be left with that term, and you get rid of the downs, and you're just left with those two terms. So on. Okay, so this says whenever you measure the one, the other one is always the opposite. Well, where does this come up? There's a lot of Bell states in nature right here. Just the two electrons in the ground state of helium in that first shell, they're in a state like this. But let's say we have something like a pion. Remember, we went through a pion. Pion, it decays into two gammas. One goes this way, one goes this way. Now, the spin of this is 0. It has no angular momentum to it. But the photon does have a spin. They have a spin of 1. And so what that means is one is spinning up and one spinning down. So we could just say this one is spinning up, this one is spinning down. And so one of these is an up and one of them is a down. Which one? I don't know. They're in this quantum state right here. They haven't decided what they're going to be. This thing is both an up and a down and an up. He doesn't know until you make the measurement. Once you made the measurement of this one and you say it's up, then all of a sudden that one will say, I know what I am. I'm down right here. He doesn't decide until you make the measurement right here. So that's what happens in a quantum entangled state, that they haven't made up their mind until you made the measurement. Now these could get a long ways away from each other. Maybe let's say this thing goes out to, I don't know, 10 light years away. And this one comes over here, goes 10 light years. Now all of a sudden, they haven't decided what they're going to be. All of a sudden you measure this one up, this one all of a sudden becomes down right here. How did that communication take place? That he communicated to it right there. Well, I'll come back to that in a minute right here. What happens if this is the state it's in, so this psi is equal to 1 over the square root of 2 up, down, minus 1 over the square root of 2 down, up. What if we took and measured right on this one? what state would that be in if we measured the right on this one? Well, if we're going to do that, I guess we should turn our ups and downs into rights and lefts. So if we do that, we get psi equals 1 over the square root of 2. Now we got the first up. Remember what we said up was, that was 1 over the square root of 2 right plus 1 over the square root of 2 left. So that's that first up times the down, which was the same thing with a minus here. 1 over the square root of 2 right minus 1 over the square root of 2 left. Okay, so that takes care of that one. Minus 1 over the square root of 2. We got the down, which is this one. 1 over the square root of 2 right minus 1 over the square root of 2 left times our last up, which was this term. 1 over the square root of 2 right plus 1 over the square root of 2 left. Okay. Okay, so now, what's that give me? 1 over the square root of 2. I'll just leave the 1 over square root of 2 out, and I'll put the other ones together. So what I have to do, I just have to start multiplying these out. These two give me a 1/2 right. 1/2 right. These two give me a minus 1/2 right left. Right left. Remember, the order matters. This one is always the first and that one's the second one. And then we get this one over here, plus 1/2 left right minus 1/2 left. Okay, so that takes care of that. We're pulling out this 1 over the square root of 2. I got to remember there's a minus there. So when I multiply these two, it's a 1/2 right, but there's a minus. So it's a minus 1/2 right. Then these two, it's also going to be a minus 1/2 right left. Minus 1/2 right left. And then we've got these two. We got a minus, so it's a plus 1/2 left right. Plus 1/2 left right. And then we've got the last term. Minus is a plus 1/2 left. Plus 1/2 left. Okay. So now we just combining terms here. Here I've got a 1/2 right, and I got a minus 1/2 right. So those two are gone. I got a minus 1/2 right left, minus 1/2 right left. So that's just minus right left. So I still have the 1 over the square root of 2 minus right left. I guess I'll write it like this. Minus right left. So that took care of this term and that term. Here we get a minus 1/2 left, and we got a plus 1/2 left. So they're gone. And then I have these two terms here, which is 1/2 left right plus 1/2 left right, which is plus left right. Or if I multiply the 1 over the square root through, we get 1 over the square root of 2. Maybe I'll put this term first. Left, right. Actually, I'll write it like this. 1 over the square root of 2. Left, right. Minus 1 over the square root of 2. Right, left. Well, that looks like if I measure the first one right, the second one automatically becomes left. If I measure the first one left, the other one becomes right. So over here, if I measure this up, this one becomes down. If I measure this one right, this one becomes left. I guarantee if I measure this one in, this one all of a sudden will become out. Boy, there seems to be something going on between here and here. Now, there was a big debate in the 1930s, right here. 1930s. Einstein did not like this, right here. Why? Because there's something in physics called locality. Locality. That says the only thing that can affect this is things that are nearby that can get there within the speed of light. So, you know, if you're within 1 light second, you can get there within a second, but if you're way out there, you can't affect this. If there's a star 10 light years out there, it's going to take 10 years just for the signal, any signal to get to it, so it can't affect it right now. You know, it takes 8 minutes for a signal from the sun to get to us. So there's no way we could get a signal faster than that 8 minutes. I mean, even if you took away the sun, we would continue to orbit nothing for 8 minutes, and then we would go off in a straight line. So this locality thing says, you know, you can't be affected by things that are way outside your region. And so he says, this can't be right here. What Einstein, it was actually 3 people, Einstein, Podolsky, and Rosen, wrote a paper in 1930s, around 1935 or so, called the EPR, where they said that, no, what these objects have to have is something called hidden variables. So there has to be something called hidden variables. That is, this guy, even though if we measure this up, he has to have something in him that we haven't been able to detect that says he's going to be an up, which means that he didn't have to get it from this guy over here. So he was going to always be an up right here, if that was the case. And so to get away from this locality, because you don't want to say violating locality right here. And so there was a big debate. Bohr was the one that said, no, they can send this signal over. Now, you're not violating special relativity because you're not sending a signal. Because you can't affect the measurement there. You can't affect, if you can force this to be an up, then that would be a down. But you can't force this to be an up. All you can do is measure what's there. Well, so there was a lot of big debate, still probably debate going on now, as to whether this can affect that over large distances. But it actually got answered in about 1964. Someone by the name of John Bell. That's where we get these Bell states from. John Bell, 1964, this was 8 years after Einstein died and a few years after Bohr had died. So he actually proposed that there might be a way to determine whether this signal actually transverse across the universe or across the galaxy and back to see if there's actually any hidden variables or not hidden variables right here. So it's either this or it's quantum mechanics right here. So what Bell proposed is he actually proposed something. He said, let's assume that Einstein, Podolsky, and Rosen were correct. Let's say the universe holds to this locality. And let's assume we have quantum entanglement. So you got quantum entanglement. All quantum entanglement means is that this state and this state are opposites. Why? Because the total angular momentum has to be 0. So you get entanglement. I mean, I should just say entanglement. So you get entanglement and you get locality. By these two things, you have to have hidden variables. That's what he said. Let's assume these two are true. You have to have these hidden variables. And so how can we determine what you should get here if we did some thought experiment right here? Well, actually, it doesn't even have to be a thought experiment. What he did is says, let's come back to this device right here, where it gives off these particles right here. And they could have been, well, I guess they're photons, but we could have, since we're dealing with photons, we could have put polarizers here at different angles. If they were electrons going off, and because you can get Bell states with electrons too, we would put our sensors, well, I guess our sensors, at different angles right here. So what we're going to do is we're going to measure these guys right here at two different, each time for different particles, we'll measure them at two different angles, either up, right, left, down, whatever. So let's just say this is, well, over here we'll measure, this is particle 1, this is particle 2, and we'll do it over here, this is A and this is B, this is C and this is D. And so when we make a measurement, we're going to combine two of them. We're going to say, how much does, say, A and D agree with a certain measurement? You measure, for this state, you measure A and you measure D. So and then you'll do it for A and C, B and C, B and D. And we'll just do it for all, look at the possible combinations. Remember, Bell is going to assume that this is all true right here. And if things are true, that means once this particle leaves, he can't change whatever he is. He has to stay whatever he is because there's no communication going on. Okay, so what does he have to do? He's going to compare A with C. Let's just say you're going to compare, say, the probability that A and C agree. Right here, A and C agree. This is an agreement. And then you could do it for the probability of, say, the B and C. And you could do it for the probability of B and D. They agree. So you're going to have to set up one experiment, look at A and D, A and C, B and C, B and D. And the last one is A and D. Okay, so those are that's going to be your experiment. You're just going to try looking at probabilities for these 4 possible combinations right here. Now, let me just say, suppose that the A and C agree, let's say 85% of the time. I'm just going to make up. Suppose they agree 85% of the time. And B and C, let's say they agree all the time, 100% of the time. And let's say that B and D agree 85% of the time. And then we could ask, how much does A agree with D? So, if I look, and we just say A, C, B, D. If we look at how much they agree, we already know C agrees with B 100% of the time. And A agrees with C 85% of the time. And B agrees with D 85% of the time. 85%. So A and D must agree quite often, just by looking at that. If this is going to agree with C, and C agrees with B 100, and B agrees with D 85, this is going to have to agree with that quite often, right here. Now, one way we could do it is not say how much they agree, but how much they disagree. You know, where's all the disagreement come from? You know, here, you notice they disagree 15% of the time. So there's already at least a 15% disagreement right there. And there's zero disagreement here, zero disagreement. And across here, there's another 15% disagreement. So, at most, so that means the total disagreement is probably on the order of less than or equal to 15%, because this is the most you could disagree. So the probability of disagreement, the total disagreement has got to be less than 30%, or the total agreement must be greater than 70%. If you disagree less than 30%, then probability of A equal to D has got to be greater than at least 70%. This is what's called Bell inequality right here. It's just what the probability has to be for these measurements right here. It's just a statistics game right here. Okay, so this is assuming that locality exists. There's no communication between these two. That's what you should get between A and D. If these were the probabilities individually, right here. Okay, so now let's go to the quantum realm right here. You remember the quantum realm, we had this block diagram right here. Now, suppose we take out the in and out. Let's just stay on this upright, left down plane right here. If you're staying on that plane, then phi is always 0. And so then we just have this right here. We just have cosine theta over 2 up plus sine theta over 2 down, if you're just on this plane right there. And let me just draw that plane right there over here. So we have... So we got up, we got up, we got right, and we had down, and we had left. So in and out is this way, but we don't care about in and out right there. And we already know that on this plane phi is always 0, so we know that psi is equal to the cosine theta over 2 in the up plus sine theta over 2 in the down. Well, suppose one of your states is right here at some angle, say alpha. This is your state psi. And your other state is straight up. And now you ask, what do you get for the probability between this state and that state? So all you're going to do is you're just going to take the probability between this and up, which is just up psi squared. Now you already know when you do the up with the down, you get 0. When you do the up with the up, you get 1. So this is going to be cosine theta over 2, but then you square it. So this is going to end up being cosine squared alpha over cosine squared of alpha over 2. Alpha over 2. Right there. So that's what it's going to be. Now, so if you're off by, let's say this is off by, between here and here, you're off by 45 degrees. So I'll just put in, if alpha is 45 degrees, then you get cosine squared of 45 degrees. Cosine squared of 45 is 0.85. So this I'm making a column of cosine squared of alpha over 2. What happens, well, actually, let's do 0 degrees first. If you're at 0 degrees, cosine of 0 is 1, which would make sense. If you're right here, if they're both right here, then you just get up, up, and you get 1. But now, if this is at 45 degrees, we just said that's 0.85. What if you're at 90 degrees? If you come over here to 90 degrees, cosine of 45 is 1 over the square root of 2, but squared, that's 0.5. So at 90 degrees, you get 0.5. Which we already knew that because we already said if you're in the up, what's the probability of getting right? It's 50%. Okay. Let's keep going. Let's take the 135. I don't know if we need that one. Go another. That means that you're way down here between here and here. That'd be the cosine of 135 over 2 quantity squared, and that's your 15%. And now let's go all the way to 180 between here and here. 180. Well, if you plug in 180, that's 90. The cosine of 90 is 0. That's 0. So, remember, up, down, give you 0 when you dot those two. So, okay. So, now, suppose, now that when we're going to do this experiment, we might as well see how we got these 85%. Suppose we do our experiment this way, right here. We put one of our polarizers, or whatever you want to be, our sensor is straight up. Okay, that's my A. My B is going to be off at 45 degrees. So there's my B. He's going to be tilted. So A, the sensor was this way. B is the sensor is this way. C, it's going to be going down. This was 45, 45. And there is C. And he's also at 45. And D will be over here. D. So these are, so on the one side, the C and the D, one of my sensors is this way, one of my sensors is this way. Over here, one of them is this way and one of them is that way. Okay. So now, if I just ask, what is the probability of A and C? Well, if A is up, if this one is up, what should the other one be? The other one should be down. Why? Because these two are always opposites. So if the first one is this, the second one should want to be right here because it's the opposite. Remember, it's a quantum entangled state. Well, how far am I from C? Because I want to do A and C. Well, between this guy and C, you got 45 degrees. 45 degrees is 0.85, which is 85%. So it coincides with this right here. Now, what about between B and C? Well, B was this way. C is this way. Well, heck, they'll always agree because no matter what this state is, this one is always the opposite. Remember, if this one was right, this would be left. If this was up, this was down. They're always going to correlate. That's going to be 100%. So it's going to be exactly like this one right here. And then the last one, B and D. Well, if B is this way, the other one would be down here. Now you have to say, how far am I from D? Well, I'm this distance, which is 45 degrees from where I should be to get 100%. Well, 45 is another 85%, which is exactly this right here. So far, the experiment is exactly like this one that Bell said right here, where he assumed locality and hidden variables. And then when he calculated A equal to D, he said this inequality has to be true. This A equal to D has to be greater than 70%. Well, what do we get for A and B? Well, A is this way. The opposite of A would be right there, and we just want to know how far is that from D? That from there to D is 90 degrees, so the probability of A equal to D 90, that's 0.5. Which means that this is being violated right here, which means that this is assuming locality and hidden variables is all wrong right here. This can't be. There is communication going on. You can communicate, well, not we. Quantum particles can communicate across the whole galaxy in no time right here, which is quite strange. I don't know what Einstein would have thought of this right here, how he would, it would have, some people think this is the most, it's quite big right here, that you can prove that particles are somehow influencing other particles on the other side of the universe right here. This is called Bell's inequality. It wasn't determined until the 1960s. He should have gotten a Nobel Prize for this right here, but I don't think he did right here. But this is quite a big thing right here. We'll come back to quantum entanglement because you need entanglement to teleport. Okay.